What's going on, everyone? Welcome back to the Panic Room. Today we are starting a new series on one of the most important concepts in network switching, the spanning tree protocol. Before we build a network with multiple switches, redundant uplinks, root bridges, and per VLAN topologies, we need to understand the basic problem that spanning tree was created to solve. And we can demonstrate that problem with only one switch, one Ethernet cable, and one potentially terrible decision. Let's jump in. Let's start by asking, what is spanning tree? I'll hit you with a definition, description, whatever you want to call it. Spanning tree protocol is a layer 2 protocol that prevents switching loops. It allows redundant physical paths to exist while creating a loop-free logical topology. That distinction is important. The cables may physically create multiple paths, but spanning tree determines which path is allowed to forward Ethernet traffic. For this video, we're keeping everything on a single switch. We are not electing a root bridge between several switches just yet. We are not configuring bridge priorities, and we are not discussing different spanning tree instances for different VLANs. Today, we are just going to concentrate on what a layer 2 loop is, why it's dangerous, what BPDUs do, and what's happening to a switch port as spanning tree evaluate. So let me hit you with a little reminder regarding the OSI model. Spanning tree operates at layer 2. At layer 1 we deal with bits, layer 2, where we are, frames, layer 3 packets, and layer 4 is commonly TCP segments or UDP datagrams. We just say bits, frames, packets, segments. You have to memorize that because on any type of exam, CCNA, Network Plus, they are going to ask you about that. So just do your best, commit that to memory. Bits, frames, packet segments, and for a spanning tree, always layer 2. So as we said, spanning tree was created to help prevent loops, help keep redundant links up and functioning properly. So what is a layer 2 loop? A layer 2 loop exists when an Ethernet frame has more than one continuous path through the switched network and can return to a switch repeatedly. The simplest lab example is taking both ends of an Ethernet cable and plugging them into the same switch on different interfaces. Now, nobody's gonna casually walk into an IDF or your network closet and just plug, an Ethernet cable into two different ports. That'd be weird. And depending on the circumstances, it could look suspiciously like a premeditated denial of service attack, but similar situations can happen accidentally. Someone may connect both wall jacks in an office with the same cord to an unmanaged switch, which would cause problems. A patch panel connection may be incorrect in the data closet. Someone may connect two switch ports together while just trying to troubleshoot. Or someone may install a second cable for redundancy without understanding that redundancy at layer 2 can create loops. There are too many different ways this could happen, so we'll just throw a few out there and just go with that for now. So let's try to understand why loops are dangerous. Imagine a computer sends an ARP request. An ARP request is carried in a broadcast Ethernet frame. When that switch receives the broadcast, it forwards it out every applicable port in the VLAN, except for the port it arrived on. Normally, that's just regular behavior. That happens every day. No one even knows it happens, but it does. But when a loop exists, that broadcast frame can return to the switch through another port. The switch receives it again and floods it out again. And then it comes back again, and the process continues over and over. Ethernet frames do not contain like a layer 2 equivalent to layer 3's time to live field in the frame. An IP packet's time to live is decreased by a router, not by a layer 2 switch. But while a frame is being switched around the inside of the same layer 2 domain, there is no time to live value naturally counting down to 0. That means the frame can continuously circulate until something interrupts the loop. As more broadcasts and unicasts traffic enter the loop, the switch may create and forward more copies. This can result in things like a broadcast storm, link saturation, high CPU utilization, definitely packet loss because disk cards are going to start flying out the window. Unstable connectivity, stuff's going to start falling off the network. And MAC address flapping. Now, MAC address flapping is something you will see, and hopefully I'll be able to replicate that on the switch I have on the screen right now. It literally says MAC flapping. So, what is MAC flapping? A switch learns a device's location by examining the source MAC address of the incoming frame. It associates that MAC with the port where the frame arrived. But during a loop, that same frame may return through different ports. So what's really happening is the same update for that MAC address is being sent through repeatedly. So on that device's port 1, it's thinking, no wait, I just seen that on port 2. Oh wait, never mind, I seen that frame back on port 1, and so on. And that's where the flapping comes back and forth. That's called MAC address flapping or MAC address instability. Once that switch can no longer maintain a stable understanding of where devices are located, regarding interfaces, traffic forwarding becomes unpredictable. And this is one of those incorrectly connected cables can disrupt an entire VLAN. Bring networks down, that's where it all begins. All right, attempt number 2 at showing you the dangerous portion of this demonstration. I have this switch isolated from my production network. It's kind of on its own island. I have a couple devices plugged into it doing pings on interface 2 and 3 just to generate some traffic. Port 5 and 6 are the same Ethernet cable. So right now Spanning Tree is doing its job, but I'm going to show you what happens when we take Spanning Tree off VLAN 5. We'll just type no Spanning Tree VLAN 5. We'll see a bunch of console messages. We'll do a show Spanning Tree as this is happening. Oops, we're in config mode. No Spanning Tree exists. So let me do a show proc CPU history. So what that's going to show us, this top one is in seconds, it's just going to show us that the processor is going to climb because it's just being saturated. It is, the broadcast storm is happening right now. Those other two devices on interface 2 and 3, they were just pinging each other. They are not pinging anymore. I wish I could get that over here in the video, but I don't have OBS on those devices. So let's do a show proc history. You can see it is just climbing. So I'm gonna put Spanning Tree back on VLAN 5 for right now, just so I don't lose access to my switch and have to actually reboot it. Go back in the configure T, and from here we'll just do Spanning Tree VLAN 5. We'll do a show spanning tree. And there we go. As you can see right here, we have the 3 ports in listening, because they are listening for the next prompt. Okay, now they are learning. We'll go over these states in a little bit. It's learning all the other MAC addresses and switch port states. Okay, we're back. The broadcast storm is over. We made it through. All ports are in forwarding, and we are blocking the one other cable. Like I said, interface 5 and 6 are both plugged into the same switch. So if we wanted to take a minute to reflect on what just happened, depending on all the different types of traffic that could be on a production network, things we would notice is all the interface counters would just start climbing like crazy. Broadcast traffic repeating, MAC addresses moving between ports, flapping, and definitely the high CPU like we've seen, and definitely loss of network responsiveness. So if I look over at my other devices, the ping had come back. So as soon as we re-added spanning tree and it settled down, everything came back. But in this controlled environment, it's easy to do. Out in the field, a real scenario that, I don't want to say I ran, because I didn't run. I just, I made a walk a little faster than normal. But I had a user that decided to move themselves. And now, in most enterprise environments, you have a nice handset for your phone. And those voice over IP handsets, they allow you to plug one cable into the network jack on the wall, and that's how you get your network, and then your computer network cable plugs into the back of the phone. It's called a pass-through port. Now that allows 2 different networks, so your phone will be on your voice network and your computer will be on your data network. That pretty much comes bare minimum with pretty much all switches out there. But what could happen is that user doesn't know better, because they're not, an IT person. So they just put all the cords behind the desk. They're all dangling down. They say, oh, there's 2 or 4, network jacks in the wall. There's 2 data cables. They just plug them both in. Now that top port was for the phone, and then for the computer to go through the pass-through, and the bottom jack on the wall was for the printer. They don't know that. So now what they did was essentially plug the same data cable into the same switch. And that's how, for that network, things would become very slow at first. And then that whole switch stack would eventually be unresponsive, just because the processing on it would be maxed out, right? That would be like your computer running at 100% CPU. It might remain on, but try to do anything on it is going to take a long time. I guess we can step into what BPDUs are and what they do. When I turned spanning tree back on, let's back up just a few seconds. So when spanning tree was off, no BPDUs were being sent. Okay, so BPDUs are bridge protocol data units, and they are, pieces of data that are talking to all the other switch ports to kind of understand where they're at. If they're in their learning state, blocking state, forwarding state. So, no spanning tree, no BPDUs, no figuring out what's going on. As soon as we turned it back on, spanning tree VLAN 5, BPDUs started going out, trying to figure out why the broadcast storm was happening. BPDUs contain information that allows the spanning tree capable switches to identify the topology and detect redundant layer 2 paths. So a layer 2 path, like I said, that same data cable plugged into 2 switch ports on the same switch. Even on a single switch, a BPDU transmitted from one port can return through another port, creating that loop. That tells the switch that there are two ports that formed a redundant path. Spanning tree can then prevent both those switch ports from forwarding normal traffic. Puts one in blocking state, one in forwarding state. So I was just about to show you what happens when spanning tree is enabled, and I was going to plug in the other side of the data cable. So let's look at what's going on. See if we have nothing. So we have nothing, right? We have my two devices off to the side. We're dealing with actually interface 5 and 6. Nothing's technically, it's plugged in, but there's nothing on the other end, so it's just not connected. Let's do a show spanning tree. Okay, just the two. Now, spanning tree is enabled right now. I'll connect the other cable and we'll go from there. Alright, we should see some console messages come across the screen. Notice both switch ports come up at the same time. Let's do a show spanning tree, see how fast that worked. That was really fast. There wasn't much to see there other than these two interfaces are in their forwarding state because they're okay. But switch 5 and 6 are just trying to figure out what is going on. So switch 5 is learning right now that something might be suspicious on the other end. Okay. So we went to block on switch port 6. And switch port 5 is just forwarding traffic to switch port 6. But then when it gets, I guess for lack of a better term, through the Ethernet cable and it hits that incoming port, it just blocks it. So are we using extra cycles and resources? Absolutely, for no reason. But it's not as much as if we had a broadcast storm going on. Not nearly amount. You could honestly run like this forever, and it might be years till you even notice if nothing changes in your closet. As we go through this concept of spanning tree, there are different states that the spanning tree can put those interfaces in. So we're basically dealing with just traditional spanning tree. It's 802.1d. It uses the statuses of blocking, listening, learning, forwarding, and disabled. A port in the blocking state does not forward normal traffic, just BPDUs. So it's kind of tough to understand that unless you take a second to really think about it. BPDUs, yes, they are data on the switch, but if you had your computer plugged in and you were trying to get to Google, that wouldn't work. But on the back end, there is still data flowing because the BPDUs will always work. That's the entire intent of spanning tree. During the listening, the port participates in the spanning tree calculation, but does not forward user traffic or learn MAC addresses. During the learning state, the switch begins to learn the source MAC, but still does not forward any traffic trying to go to the network or the internet. But finally, in the forwarding state, the port learns the MAC and forwards traffic just regular. Traditional spanning tree may take a noticeable amount of time to move through these states. From what I recall, it's a good 40 to 50 seconds. That's just traditional spanning tree. They have come out with rapid spanning tree, which is a lot faster. We can dive right into that next. So let me hit you with the definition for rapid spanning tree. Rapid spanning tree is defined as 802.1w, simplifies the process into these three primary operational states like we've seen under the status on the switch. So we have discarding, learning, and forwarding. That's less than just traditional spanning tree. Discarding combines several of the older non-forwarding conditions. A discarding port does not forward normal user traffic and does not learn the source MAC addresses, but it can still participate in spanning tree and process BPDUs like always. The learning port begins populating the MAC address table, but does not yet forward normal user traffic. Once it hits the forwarding state, that's when everything is copacetic again, and we will start forwarding traffic like normal. Rapid spanning tree also introduces improved port roles and faster convergence mechanisms, which we'll see more clearly once multiple switches are involved. Like I said, I'm trying to keep this one video to one switch. There is a lot to do with spanning tree, so we'll trying to break it into chunks to make it more digestible. Some of the useful commands that I didn't really explain, but we were just banging through them as we were trying to watch this switch do its thing. So I always like just the regular show spanning tree. Hit it with the show span, it knows how to populate the rest of that command, and you can see every switch port and what it's doing. So case does matter. So if I wanted to do show span pipe, right? Pipe just says only show me what I'm asking for, and I'm gonna include block. It'll just show you the one interface. Let's change that to lowercase block. You get nothing, right? Case sensitive. Keep that in mind whenever you're trying to quickly look for something. Let's do a show spanning tree VLAN 5. Okay, that gives us a little more information. That we'll get into more of this data a little in the next couple of videos. This is the root bridge. Obviously, it's the bridge. It's the only switch participating in spanning tree. So you have your bridge priority. Like I said, we'll get into that. But for now, if you have a switch and you do want to start taking a peek, by all means, check it out. So as I close out this first video in this series, I just want to recap a couple things real quick. We learned a layer 2 loop allows Ethernet frames to circulate repeatedly because Ethernet switching does not decrement any type of time to live value. So those frames naturally won't expire like they do on a layer 3 IP packet. Without spanning tree, loops create broadcast storms, MAC address flapping, saturated links, high CPU utilization, and will cause a major outage. In the next video, we'll connect multiple switches, we'll create multiple VLANs, and explain why Cisco has separate spanning tree topologies for each VLAN. I want to just pull up my packet tracer. This will be in the next video. This is just your typical learning experience right here. 3 switches connecting together, and notice that the top switch, we'll go over how it became the root bridge. We'll go over the MAC address and how to calculate that. Maybe we'll dabble in a little priority. Then we'll dive into something a little more complex, which is at your enterprise level. When you have your core environment right in the beginning, that will be always your root bridge. You have your access layer under it. And don't be worried about all the stuff on the top. That's just redundant firewalls getting out to redundant ISP paths. But we'll be focusing enterprise spanning tree. It gets a little more complicated, but we'll get there. As always, thanks for watching, and catch you in the next video.